Now let me show you a demonstration of how to solve differential equation using Laplace transforms. Before I do that, let me rewrite a few formulas that we had before. T to the n is n factorial over s to the n plus 1. And then sine of kt is k over s squared plus k squared, and cosine of kt is s over s squared plus k squared, and then e to the at is 1 over s minus a. And then there's another one with e to the at times sine kt, but we wouldn't need it today, so let me just try to use these. Oh, and by the way, the other important part was, if you take Laplace transform of a derivative, it's s times y of s minus y of 0. Okay? And if you take the Laplace transform of the second derivative, it's s squared y of s times y of 0 minus y prime of 0. Okay? All right, so here's an easy example. The first easy example. It's y double prime minus 3y prime plus 2y equal to 0. And let's say y of 0 is 1, y prime of 0 is negative 1. Let's try to solve this equation. And of course, question easy as this, you wouldn't want to use Laplace transform for this. It's probably easier just to use the older method where you do r squared minus 3r plus 2, and you solve that, and that's easier, okay? Yeah, but that's not the purpose. The purpose of solving this is to demonstrate you how to use the Laplace transform to solve differential equations, right? So let's apply the Laplace transform to each. So if I take this and apply the Laplace transformation, then because Laplace transform is linear, you end up transforming this, this, this. The constants can be pulled out. And that gives you, according to this thing here, it's s squared y of s minus s times y of 0 minus y prime of 0 minus 3 times s times y of s minus y of 0, and then plus twice of y of s equal to 0. Laplace transform of 0 is 0. All right, now we apply, we plug in the initial points, initial condition. And y of 0 is 1, so I put 1 here. Y prime of 0 is negative 1, I put negative 1 here. Okay. Let's see. You want to eventually solve for capital Y of s. So I want to collect all these terms that has y of s in there, here, here. And those should be on one side. Everything else should be brought to the other side. So I'm going to collect these three and factor the y of s out, which leaves you with s squared minus 3s plus 2 y of s equal to s goes to the other side. This is plus 1 plus 3. 3 plus 1 is 4, but when you bring it to the other side, it's minus 4. Okay? And then you have y of s equal to s minus 4 over s squared minus 3s plus 2. So we solved for capital Y of s, which seems like a solution, but it's not the solution we are looking for because we want lowercase y of t. So here's what's happening. The good side is if you apply the Laplace transform to a differential equation, you get an algebraic equation. Algebraic equations can be solved just using algebra, so it's easy. But that's not the end of the story because what you're getting is not the y of t, the thing that you're after, but the Laplace transform of y of t. So this is really the Laplace transform of what you're aiming for. And we have to somehow figure out what function it is that would produce this as its Laplace transform. That's the challenge. Okay, how do we do that? Well, one possible way is to do the inverse Laplace transform. And there is such a thing. There is this, so inverse Laplace transform is another type of integration that you don't do on the regular real line, but you integrate over some complex plane. So it's very complicated. Rather, what we want to do is just figure out a way to rewrite this as something of these type. Okay. And if you can, then from that you can figure out what it was. Okay. That's the approach we're going to take. So rather than learning this new thing, which is Laplace inverse transform, Laplace transform, we're not going to do that. We're just going to see how this can be transformed into these. Now, let's cheat a little bit. We're not supposed to do this, but if we did the old method, we kind of know what the answers will look like. What's the value of r if you solved r squared minus 3r plus 2 equal to 0? It will be r minus 1, r minus 2, right? So that gives you r equal to 1 and 2. That means y is like c1 times e the t plus c2 times e the 2t, right? And what would be the Laplace transform of this? Be c1 times e to the 1t, so if I apply this one, e to the 1t, it'll be 1 over s minus 1, right? And then this will be c2 times 1 over s minus what?
2.
2. It's e to 2t, so it'll be s minus 2. Okay, so we kind of cheated here. We're not supposed to know this. Let's pretend that this never happened. But what are we getting from here? We see that in order to get what y was, we better have it in this form. It must be something times 1 over s minus 1 plus something times 1 over s minus 2. So it looks like from that we learned that this should be represented as c1 over s minus 1 plus c2 times s minus 2. And we've done this before. When? Not in this class. Long time ago. Maybe a few months ago.
Partial fractions?
Partial fractions, exactly. So you have a single fraction, and you're trying to write it as sum of bunch of fractions. What is that called? That's called partial fractions. So that's exactly what we need to do in order to solve this. Okay. Now I'm going to erase all the red because that was just for the discussion. So I'm just going to erase all the red writings. Okay, pretend that never happened. And I'm going back, and I'm going to do this. I'm going to say y of s, if you factor the denominator, it's s minus 1 times s minus 2 with the top being s minus 4. And therefore, using the method of partial fractions, I know that this can be written as something over s minus 1 plus something over s minus 2. And then I have to figure out what a and b are. Okay? So let's do that. You can combine these two into a single fraction as what s minus 2 can be multiplied here, s minus 1 can be multiplied here. So you get a times s minus 2 plus b times s minus 1 over s minus 1 over s minus 2. And since I'm saying this is equal to that, this s minus 4, the numerator of that side should equal to the numerator of this side, right? So we set them equal to each other. So I get s minus 4 equal to a times s minus 2 plus b times s minus 1. And I have s minus 4, as minus 2a plus bs minus b. Combine the two things with s's, so s minus 4 equal to a plus b times s minus 2a minus b. So that means a plus b must match with 1, which is the coefficient of s, and negative 2a minus b must match with negative 4, the constant terms. And you just have to solve these. You have two unknowns, a and b. You have two equations, so that means you can solve this, right? I guess the quickest way to solve this is just to add them, because if you do that, you get negative a on the left side. B plus negative b gives you 0, so that cancels away. A minus 2a is negative a. On the right side, it's 1 minus 4, this is negative 3. So a must be 3. Okay? And on the other hand, if I plug in 3 back in here, then I get 3 plus b equal to 1, which means b is equal to negative 2. So I got these values. What do you do after? You go back and replace a and b with the things that you figured out. A is negative 3, no, positive 3. And then b is negative 2. And that, in turn, will tell you what y of t is. What is y? It must be 3 times. Which one gives you 1 over s minus 1, according to this?
E of a of t.
Either 1t, right? Either 1t. So it must be either 1t plus negative 2 times. Which one gives you 1 over s minus 2? What? E to the what?
E to the 2t.
E to the 2t. That's it. That's how you solve it. Right. Okay? Now, let me just add a little more note to our solution here. Sometimes you can take some shortcut with the algebra part of getting a and b by first multiplying the denominator both sides and then plugging in values for s. Okay, so let me write a short note here. So note, if you had s minus 4 over s minus 1, s minus 2 equals to 3 over s minus 1 plus negative 2 over s minus 2, then, sorry, I should have these as a and b. And let's say I want to find out what a and b are. Okay. Here's a slightly quicker way of finding a and b. First, multiply this denominator both sides. What happens if you do that? If you multiply s minus 1, s minus 2 both sides, that has to be multiplied to everything. then you see that these cancel away, this cancel away, and that cancel away. Okay? Now I wrote all this down, but you can definitely do this without writing it down. You can just say, see this and say, what would happen if I multiply this? Well, if I multiply this, this is going to go away in the left side, but on the right side, if I have s minus 1, it will be s minus 2 that survives. On this side, it will be s minus 2 that cancels, leaving you with s minus 1. Okay? So can you do that without having to write all this? Yes, right? And then what you do is you say s minus 1, no, s minus 4 equals to s minus 2 times a plus s minus 1 times b. And here's the next type of reasoning. The next type of reasoning says, well, you know what? This is equal as functions. See, this is a functional equation. Okay? It's an equation between functions. I'm saying this function and that function should be exactly the same. But what does it mean for two functions to be same? It means that for any value of s, whether you plug in s equal to 1 or 2 or 3 or whatever, both sides should produce the exact same value. Isn't that right? So what you do is you can plug in 1. Let's see what you get if you plug in 1. You get negative 3 on this side. 1 minus 2 is negative 1. 1 minus 1 is 0, so you get this, and you immediately get a equal to 3, which was the result that we got before. And then you can plug in s equal to 2, and that's 2 minus 4, which is negative 2. 2 minus 2 is 0. And 2 minus 1 is 1, so you get b. b equals to negative 2 is immediate. Right? So you can use this fact that they're equal as functions, and therefore you're free to plug in whatever. Usually you want to plug in the values that will make some of these equal to 0. Okay? So I've shown you two different ways of getting these coefficients. One is to organize each side in powers and compare the coefficient. So you can compare the coefficient, or you can also plug in values. There are two methods: coefficient comparison and plugging in. Those are the two methods.